Here we are in SPSS 24, and what we're going to do today is we're going to work through the logistic regression examples from Chapter 8 in your textbook. And so we're going to be using the General Social Survey data, which I believe you have probably seen before a few times. So I'm just going to go open up my copy of it. File, open data. There we go. Excellent. Just quick double checking, make sure I've got the right thing up. All right, so what we're going to do is we're going to go through the process of running a logistic regression using a handful of variables within this data set. I'm going to be doing almost exactly what is in your Chapter 8 text with one exception. Not that it's going to matter in this first example, but we will not be allowing the logistic regression tool to create our dummy variables for us. We are instead going to create our own when that becomes necessary. So you can follow along at that point as needed. What we're going to do is try to determine to what extent gun ownership varies by certain variables. Now, how you interpret logistic regression is different than regular linear regression. In regular linear regression, each increment in your independent variables should lead to certain amount of increment in your dependent variable. In logistic regression, because your dependent variable is a categorical variable that has been coded 0 or 1, what you are really looking at here is a probability, basically. Although logistic regression does something a little bit different, it creates something called log odds, but that can be turned back into a probability for the purposes of interpretation. And obviously we'll have talked about this a little bit in class. So you know you have to start out with a dependent variable that is categorical. And in this example, that variable is owngun, O-W-N-G-U-N. And our dependent variable in this case is going to be Polviews, P-O-L-V-I-E-W-S. So this is a bivariate logistic regression. Two variables. It's the equivalent of simple linear regression, except we are using a categorical dependent variable. Therefore, it is logistic regression, but it is a simple bivariate example. All right, so according to your text, the first thing that we want to do is go take a look at the owngun variable, making sure that it's what we think it is, a 0-1 binary variable. While we're at it, I'm going to go ahead and look at the Polviews variable, making sure that it is an ordinal variable, a scale that runs from 1 to 7. A scale with that many categories is appropriate to use as a continuous variable for the sake of doing regression, so we'll be fine with that. But we just want to double check. It's always a good idea. So I'm just going to do descriptive statistics frequencies, and I'm going to find the two variables that I'm interested in, which are owngun and Polviews. Here's our owngun, and then we need Polviews, which is shortly after that. SPSS, you may know this already, uses these little icons to distinguish between something that is categorical and something that is going to be ordinal or continuous. Something along this is true continuous right there, the little ruler, but that's going to be ordinal. All right, so we have what we're looking for here. I could go ahead and do more detailed, making sure that I'm looking at all the information I need. Our mean, median, mode, standard deviation, to do a full descriptive statistical analysis of my variables before I move on into my logistic regression. Always a good idea, never hurts. Okay, we'll just go with that. All right, so have gun and home, think of self, mean, median, mode. Yeah, I was looking for this just to see how many missings we were dealing with here. Quite a few, actually, for the own gun. All right, so owning gun, no, yes. Excellent. These are all coded as missing, the IOP, DK, and refused, and that adds up. And then here's our scale for liberal or conservative, and the various missing. So I'm happy to move on now to doing my bivariate logistic regression. So just like in linear regression, it's analyze, regression, but you're going to come down here and choose binary logistic. And at this point, we want our dependent variable, and covariates is the term used for independent variables. So my dependent variable is going to be own gun, which is down here a little ways. There we go. And my covariates are Paul views. They go right there. We're doing the straight enter method. I don't need to select out by any variables in this case. If I needed to work out something with my categorical variable or some options, I could do all of those, but I'm actually not going to. I'm just going to go straight to OK. And now we have our results. And these are exactly the same as the results that are in your text on page 193. You've got a little bit of a case processing summary. You've got sort of proof that your no is a 0 and your yes is a 1, which is important in logistic regression, that the existence of the characteristic in the categorical variable gets the 1. Here we've got a classification table and other variables in the equation, and this again matches up exactly with what we're seeing in page 193 of your text. So it's actually this one down here that we're interested in. This looks a little different because by default in my SPSS it's giving me the label rather than the variable name. I could change that if I needed to. In case you have forgotten how, we would come to what would we come to? I'm looking for preferences. Yeah, we'll come back to that later. I should just cut that right out so you don't know that I'm like flailing around trying to find my preferences. Ha, there's a reason. You get that one here under your data view options right there. It's the ability to switch over from having labels versus names. All right, so back on task here. Here's our results. So we consider this interpretation of the regression coefficients here, the B's, as what are called log odds. Not always the easiest thing to understand. We do know the direction is positive. 2.68 is a positive number. They represent the difference in the log odds of the dependent variable for each 1 unit change in the independent variable. So as you move up that scale of political views, you get an increase of 0.268 in your log odds of gun ownership. It's sometimes a little bit easier to look over here at this, which is it's the anti-log of this. That is, this has been naturally logged. This is that to the power. Undoing it using anti-log, or as I do it in Excel because I don't really have a calculator that will let me do it. But here I don't have to. SPSS has done it for me. All right. The odds ratio is the coefficient with the log removed, and that's what this is. That's called the logs ratio. It's greater than 1, so that means the higher you have a score on Paul views, that increases the odds of owning a gun. Each 1 unit increase in the political views scale increases the odds of owning a gun by a factor of 1.307. The last thing we want to do with our results is double check and make sure that our relationship here is statistically significant, and that is definitely the case here with that. So we have performed a logistic regression now, and we have the results we need in order to, for instance, answer a hypothesized question that the more politically conservative you are, the more likely you are to own a gun. And we can answer that question or resolve that hypothesis using this data. Now, there is more that you can do with this, and there's more you should do with this. You want to be able to kind of make predictions. You want to be able to write out your equation, which is essentially your regression equation, your and then convert that eventually to what's called a probability equation. So using your beta coefficients and your constant, negative 1.745 plus, 0.268 times whatever your value is for this variable, 1, 2, 3, 4, 5, 6, or 7, equals the, in this case, what are called the log odds of gun ownership. Your text on page 194 through 195 shows you how to convert that log odds equation into a probability, because we can kind of understand probabilities a little bit better. You know, what's the probability of a person who has a 1 is the most liberal here owning a gun? What's the probability of someone having a 7 owning a gun? That makes total sense to think about it like that. We really understand that. In order to do that, we need to put together our equation, and I'm actually going to do that in Excel just because, you know, it's easier than anything else I might do. Plus, like I said before, I don't have a calculator that'll do anti-log for me or return to the natural number. So according to your text, your basic logistic regression equation is your log odds equals A plus B to X. So I'm just going to go ahead and do this, and then our values here could be, and this is just the way I do this. This is, you know, obviously not any special way that you would ever have to do that. It's just so that I can do the math. All right, so popping back over to my SPSS output, my constant is negative 1.7. Oops, I didn't really mean to do that, but it does make it possible for me to copy that now. There we go. And my B is 0.268. There we go. So now I should be able to just work out my equation. Now, the equation is, it's going to be constant plus beta value times whichever one of these values you're interested in. In this case, I'm going to say, okay, the most politically liberal. You know, didn't quite work for me there, and I think that's because that is not accurately in here. E17 plus E18. Okay, fine. I probably just need to stop my screencast now and start over so that this is a little less weird for you. But I just want you to show that, you know, even we all struggle with this kind of stuff. So if you go through what's on page 194, this process of kind of working your way down through the equation, you'll notice that you don't ever actually need to use that first equation. I'm going to figure something else out for you here. So if our probability is the exponent of A plus B times X over 1 plus the exponent of A plus B times X, then what you end up needing to do is how do you get that anti-log? How do you pull that logged value back into a natural value? And there's a formula in Excel that does that. So in our case here, with our full equation, I'm gonna go ahead and put this out. What we need is our negative 1.745 plus 0.268 times 1. I'm going to do 1. Your book example does 7, and I'm going to do the opposite of that. So the most liberal person is what I'm going to do here. So part of the reason why I'm going to do that is because 0.268 times 1 is 1. So we've got equals negative 1.745 plus 0.268. There we go. And we are going to want to unlog that a little bit. So we need to use a function called exp. Pretty straightforward, exp, and I'm just going to pop it right in there. I'm not going to retype it. And there we go. Our exp is 0.2. All right, so if we're using our equation now, it's that value over 1 plus that value. So I'm just going to completely round this off here, and I'm going to say I want 0.23 divided by 1.23. There. 0.1869992. Essentially what we've got going here, we round that down, 0.19. The probability of a very liberal person owning a gun is 0.19. And so I realized that was a little bit scattered of a way of doing this. But I was just showing you, the point was to show you that if you don't have a calculator, you don't want to do this necessarily by hand with, like hand calculating everything. I didn't even have a well-organized sense of doing this in Excel. I was using Excel as my calculator here and working my way through the equations here on page 194 and 195. That's what you're going to be expected to do. If you use a logistic regression method, not only do you need to be able to talk about, are your relationships significant? What are your beta values? What are your probabilities? What's your you also need to be able to write out, what's your equation, and can you use it? I mean, we all know that regression is not a perfect method of predicting anything, but we do use the word prediction in this case. And if we wanted to come up with a probability of gun ownership based on somebody's choice here, that equation produces that for us, and that would be another part of our results. Now, often another thing that happens is that you graph your logistic regression line in order to get a visual view of how closely your model fits. We're not going to be doing that here today. You're not going to be expected to do that right now. So we're not going to proceed on to that part in the chapter. However, our next goal is to be able to do a multivariate logistic regression, that is, where we have more than one independent variable for our one dependent variable. And that'll be part of your next video.